Hello everyone. In this session, let me explain last theorem in unit 3. So this completes, if I do this theorem, so this completes unit 3. So in the next section, I will be starting with unit 4. Before that, I have already I have already told you about the test. So whatever the questions there is there in the question paper, you have to practice the same question and you have to write at least one questions per day. So in alternative days test will be given. Please follow up the same and please write all the questions in the only one book, that is keep one blue book and you keep on writing the questions in the same book and please upload it in a form of PDF. Fine. Now let me explain the theorem. This is important theorem and it is asked in the year 2016 as well as 2018, and whatever the theorems statements I have written here, both the statements are equivalent. Either you can get this statement or you can get this statement, but not both. Please make sure that given statement in the examination. Now coming to the proof, so in the given statement itself, it is given a bounded function f defined on a measurable set E of finite measure is leberque integral. So if and only if f is measurable. So we have to prove both the parts. So let me assume that is given a function f from E to R is bounded, right? Bounded and E is measurable. Whatever the given data, I have written the same. Fine. Proof. Given that f defined from the set E to R is bounded and moreover E is a finite measurable measure. Now we have to prove f is leberque integral. When do we say f is leberque integral? So as per the given statement, only if it is measurable, right? Suppose f is leberque integral. Let me assume. Let's suppose f is leberque integral. What I'm trying to prove is, I'm trying to prove it by contradiction method. Like what I have assumed is f is leberque integral. What I'm going to prove is f is measurable. Clear? First part I'm proving. The theorem is somewhat lengthy, but if you understand the concept well, you can practice. Fine. See here, what I have assumed is given data f is bounded function and E is measurable set. I have written here. Now what we have to prove is if it is leberque integral, only when f is measurable. What I have assumed is f is leberque integral. So what I'm going to prove is f is measurable. So let me suppose if f is leberque integral, as per the definition of leberque integral, what it says, so it is the representation of leberque integral, right? It is the leberque, we pronounce this as leberque integral of a function f over E. So if supremum of a given function with reference to simple function, I'm going to write simple function pi is equal to infimum of all the simple functions psi is equal. Then only we can say a function f is leberque integral, right? So whenever a supremum of a simple function pi and which is equal to infimum of a simple function psi, then we can say function is leberque integral. So let me take dx, right? So let me take this as I. Fine. And let us consider this as equation 1. And moreover, a condition will be obvious as per the definition of simple function, leberque integral in terms of simple function. There I have clearly explained that pi n is less than or equal to f and psi n will be always greater than or equal to f. Why? Because psi is with reference to infimum, that is why I have taken greater than, and pi is with reference to supremum, that is why I have chosen less than or equal to. Hope so it is clear. Now I have defined the two function pi n and psi n, and they are in such a way that integral over pi n of x into dx will be greater than I minus 1 by 2n, where n is small quantity, so you can assume that, and psi n will be psi n of x integral over e dx will be less than 1 plus 2n. Why? Because pi n is with reference to supremum, right? Pi is with reference to supremum, so it is the maximum value, that is why I have taken greater than here. Fine. And psi is with reference to infimum, so that is the reason I have taken less than. So I have defined two functions, simple function pi n and psi n in this manner. Clear? Now what I am trying to prove is f is leberque integral. Now let me set pi star as supremum of all the pi n's. Here pi n is a simple function. If you are going to take supremum over all those, you will get lower leberque integral. If you are going to take infimum over r psi n, you will get infimum. Now I am going to set pi star, which is a new simple function, which is in such a way that it is a supremum taken over all the pi n's, and psi star will be infimum taken over all the psi n's. Fine. Then both the measurable functions are in such a way that, in the sense, f will be in between pi star and psi star. That is, I can write pi star less than or equal to f less than or equal to psi star. So I have defined two functions such that pi star is supremum of all pi n and psi star is supremum of all infimum of all psi n. Now let me consider a set A as set of all the elements of E, moreover E is measurable, such a way that pi star of x is less than psi star of x. So this value is less than psi star. So I have considered all those elements as A. And let me consider AR as set of all the elements in E for which pi star of x is less than psi star of x minus 1 by r. Similarly, let me consider a set A r comma n as set of all the elements of E such that pi n of x will be less than psi n of x minus 1 by r. Fine. Now you can note from these three defined set, clearly I can make an observation that A will be equal to union of all the ARs. Right? See here, why? Because A contains an element of the form pi star less than psi star. Since I have subtracted only one element from this, that is, it is previous element. Something like if n is an element, if it contains in one set, previous element will be n minus 1. It is also belongs to same set. Right? So I can express A as union of all ARs. Clear? So these are all basic concepts which is there in a set theory. Now, and second observation is that AR is a subset of AR comma n. AR is subset of AR comma n. Why? Because it contains elements more or less in the same form, but the function is only different. Function is different, but all the elements will be of same form. So I can say AR is subset of ARn. I mean, it contains part of ARn. And moreover, measure of ARn will be less than r by n. Whenever you are going to take measure over this set, will be less than r by n. So this is obvious. Suppose that if I am going to, I just prove it by contradiction method. Let me assume that if measure of AR comma n is greater than or equal to r by n. Actual condition is that if you are going to take measure over ARn, it will be less than r by n. So whatever you are going to take a measure over such kind of element, obviously it will be less than r by n as per the properties. Now suppose if it is not possible, I am going to prove it by contradiction method. Let us assume it is the elements will be, measure is greater than or equal to r by n. So if this is the case, I am just proving it by contradiction method. So let me write here, and before that, this is what I have, right? Since we already defined pi n and psi n here, so if you're going to take, let me take a difference of those two sets. I mean, when I'm going to take integral over E psi n of x into dx minus integral over E pi n of x into dx. Make sure all this calculation will not be there in the notes, so you have to go through the video for better understanding. Now sin of x is, I'll just simplify here. I can write this is less than 1 by 2n minus pi n is what we have, it is 1 minus 1 by 2n. If you're going to take difference, what you're going to get, 1 plus 1 by 2n minus 1 plus 1 by 2n. So plus 1 minus 1 get cancelled. It will be 2 divided by 2 by n. In the sense, whenever you're going to take a difference of psi n of x with pi n of x, difference is always less than 1 by n. So let me take this as equation 2. Fine. Now, whatever the sets I have assumed, now I am going to take the same difference with reference to this set. Now let me consider pi n of x with reference to pi n of x into dx with reference to ARn. So whatever the set I have ARn, since measure of ARN is less than R by N, so I am going to take with reference to ARN. So sin of x into dx minus pi n of x into dx. So if you are going to take difference of these two, let me see what will happen. So I can write this as pi n of x, sin of x minus pi n of x into dx. Now whatever the difference you are going to take, as I already told you, it will be greater than R by N. That is what I have assumed, right? So it is greater than 1 by R times N, or else I can write this as which is greater than 1 by R times measure of ARN as per the properties that I have done in the previous session. Please go through that. Since I am removing the function which is inside the integral, so if you are doing that, we have to take measure over the set which we are going to consider, right? So you are going to get measure of ARN here. Now as we assume that measure of ARN is R by N, so what will happen? 1 by R into R by N you will get. So terms get cancelled. You will get it is greater than 1 by N. Meaning is that whenever you are going to consider a difference sin of x with pi n of x, what you are going to get? It is greater than 1 by N. Now you compare this equation 3 with reference to equation 2. What we have obtained is contradiction, right? Why? Because when you're going to take difference as per the standard definition, it should be less than 1 by N. But what we have arrived is it is greater than 1 by N. So it is contradicting the equation 2. That is what we have assumed, that is measure of ARN greater than or equal to R by N is wrong. So measure of ARN should be less than R by N. Meaning is that as N tending to infinity, that is when we keep on increasing the values of N, this value tends to 0. That is, I can write measure of ARN will be equal to 0. Now what I have assumed is ARN is subset of AR. So by that I can write measure of AR is also equal to 0. And moreover A is union of all ARs. Thereby I can write measure of A is also equal to 0. So what I have arrived is measure of A is equal to 0. So what we try to prove is we have to prove F is measurable. So when do we say F is measurable? If F is equal to whatever in terms of simple function, whatever we have assumed, that is psi star will be equal to pi star. If you prove this inequality, that implies that F is measurable. Now as per the definition of measurability, what we have assumed is pi star is less than or equal to F, which is less than or equal to psi star. Meaning is that if you remove pi star F here, you can write pi star is less than or equal to psi star. So we need to prove reverse inequality. For that I have taken this condition. So if measure of A is equal to 0, which implies that pi star of x will be greater than or equal to psi star of x. Now from these two inequality, where I have written this one, so from this inequality and this inequality both follows that pi star will be equal to psi star will be equal to F. So as I said, if they are equal, we can say F is measurable. So this implies F is measurable. So we have proved only one part, that is we have assumed that F is Lebesgue integral, and what we have arrived is F is measurable. Now we have to prove the reverse inequality, that is let me assume F is measurable and we have to prove that it is Lebesgue integral, that is F is Lebesgue integral. So let me prove here. So now let me assume F is Lebesgue integral. I am proving converse part. Fine, Lebesgue integral. Now what we have to prove is F is measurable. That is F is Lebesgue integral or F is measurable. Fine. I am just repeating once again. The given statement says that we have to prove two conditions. First one is we have to prove F is measurable, and second one is that F is Lebesgue integral. What I have proved is in the first case I have proved that F is measurable. Now in the second case I have to prove that F is Lebesgue integral. So let me prove. Since in the given statement it is clearly mentioned that F is bounded. Fine. Now let me consider the definition of boundedness. It says that in the Riemann geometry you have already learned this. So there exists m greater than 0 such that just writing the definition of boundedness, minus m less than or equal to f of x, which is less than or equal to m for all x belongs to E. So I am going to divide this interval. The meaning of this is we are going to divide the integral minus m to plus m into two equal parts in such a way that let us take the interval as x belongs to E. So k minus 1 into m by n less than f of x, which is less than k into m by n. In the sense I have divided the interval minus n and plus m such that m by n, that is, I can say that as k by n times of m. Previous element is k minus 1 by n times of m. So I have divided in this way. Now obviously E can be expressed as finite union, that is k is equal to minus n to n ek. So E can be expressed as, why? Because ek ranging from minus n to plus n. Remember, in this case ek is ranging from minus n to plus n, so E can be expressed as union of all ek's. Now let me take measure on both sides of the previous step. So you will get measure of E is equal to, so when you are going to take measure, union will become summation. So summation k is equal to minus n to plus n, measure of ek. Now for each n we divide the simple. So now for each n we can divide the simple function psi n and pi n. So let me consider the definitions as I already told you. So psi n of x will be m by n into summation k is equal to minus n to plus n k into chi of ek of x. Similarly pi n of x will be equal to m by n into summation k is equal to minus n to plus n k minus 1. I am taking over the interval k minus 1 into chi of ek of x. Fine. And moreover f of x will be in between psi n and chi n. Pi n and psi n. Fine. Now infimum, if that was the case, I can write infimum of pi n of x into dx will be less than or equal to pi n of x into dx. Right? Infimum, if you are going to infimum over pi n of x, that will be less than a single set. Infimum in the sense is set of all pi n of x. I mean one of the minimum value of pi n of x. So infimum will be less than total pi n of x. And pi n of x, what we have defined as m by n into summation k is equal to minus n to plus n k into chi of ek of x. Similarly, let me take supremum, that is infimum will be taken over psi, supremum will be taken over pi. So pi of x into dx over set E will be greater than, supremum in the sense greater than, integral over E pi n of x into dx. As per the assumption, pi n is m by n into summation k is equal to minus n to plus n k minus 1 into chi of ek of x. Now I am going to take difference of these two. Why? Because I have to prove f is Lebesgue integral. When do we say it is Lebesgue integral? Only when infimum is equal to supremum. So it is enough to show that difference will be equal to 0. Suppose if you are going to prove a is equal to b, it is enough to show a minus b is equal to 0. So that is why I am taking difference. So infimum of psi greater than or equal to f, integral over e psi n of x into dx minus supremum of pi greater than or equal to f, integral over e pi of x into dx will be less than or equal to, I am going to subtract these two terms. So m by n will be common. Summation k is equal to minus n to n. I am going to subtract k plus 1 minus k. Fine. So you will get chi of, that is, you can write this as k plus 1, k minus 1. So when you are going to multiply minus inside, you will get the same step. So it doesn't make more difference. I am just repeating it once again. See here, when you are going to take difference, you will get k minus 1. So that k minus k plus 1 you are going to get, that is what I have written here, one and the same. Fine. Into chi of ek of x. Now plus k minus k get cancelled. So what you left with is m by n into summation k is equal to minus n to plus n chi of ek of x. Fine. Now as I already told you, I can write this as, whenever you are going to remove chi of ek, you have to take measure, right? So I can write by taking measure as summation k is equal to minus n to plus n, measure of, what is the set you have here? Ek. Measure of ek I can write. Now, so measure of ek is none other than measure of E. So if you want, I will just write one more step here. So I can write this as, which is less than or equal to m by n into summation k is equal to minus n to plus n. Measure of ek is none other than measure of E. Fine. So ek is none other than, it is taken over all the sets. So it is true for one set E. It is generalized case. This is for particular case. Fine. Now whatever the LHS I have, just let me write as it is. Psi greater than or equal to f integral over e psi n of x dx minus supremum pi greater than or equal to f integral over e pi of x into dx. Now we can note that as n tending to infinity, this value goes to 0. Anything by infinity will be 0. 1 by infinity is 0. So something like this value goes to 0. So I can write infimum of psi greater than or equal to f integral over e psi n of x into dx minus supremum over pi greater than or equal to f integral over e pi of x into dx is equal to 0. Why? Because when you are going to take n tending to infinity, this will become 0. So I can write this as infimum of psi greater than or equal to f integral over e psi n of x into dx will be equal to supremum of pi greater than or equal to f integral over e pi of x into dx. So one and the same. So meaning of, as I told you the definition of Lebesgue integral, what is the meaning of Lebesgue integral? When do we say function is Lebesgue integral? In terms of simple function, only when infimum taken over psi will be equal to supremum taken over pi. So if that was the case, we can say a function is Lebesgue integral. Therefore, f is Lebesgue integral. So we have proved f is measurable and f is Lebesgue integral. So this is what the theorem is. First what I have proved is, I have proved that f is measurable. Fine. By assuming the contradiction method, I have proved f is measurable. Next I have proved that f is Lebesgue integral. Hope so it is clear. So please practice this. This is important theorem which is asked in 2018 and 2016. I'll send you the notes. Please practice the same. And this completes unit 3. So from next session I'll be starting with the fourth.